In this section, we're going to talk about graphing polynomial functions. We're going to start by refreshing what we already know about the graphs of quadratic functions. We know that they make a parabola. And so some of the important things to notice here are the location of the vertex and then the axis of symmetry. So remember, we've talked about symmetry. This black parabola here that is on the y-axis, that has y-axis symmetry. If it moves off, it doesn't have y-axis symmetry anymore, but it still has n axis of symmetry. And if it moves to the left or the right, it's going to move to x equals h. So that's going to be our axis of symmetry. Now that is an entire equation of a line, so the x equals is very important. Remember, no bald answers. So it's always going to be the x value that locates our axis of symmetry. So we're going to look at the two different forms of a quadratic. So the first one is vertex form, and this is the one where we can see all of the transformations. A is going to be a vertical stretch or shrink, H is going to be your horizontal translation, and K is going to be your vertical translation. So the parent function has a vertex at 0, 0, so it makes sense that if I shift it H units and K units to the left, right, up, down, that my vertex is now going to become HK. The axis of symmetry is going to go through that vertex, so it's always going to be x equals h. So this is just a quick refresher, so we're just going to do one example of each. Couldn't think of that word. So here's the steps to graph in vertex form. We want to think to ourselves, does it open up or down? Because that's always going to help us as far as end behavior, what our final answer should look like. And then figure out what the vertex is. Find the 2 points to the left or the right of the vertex, doesn't matter, you pick. And then we're going to reflect those over the axis of symmetry. So that's why that axis of symmetry is so important, because it will help us get the other half of our graph. We don't have to have as many points because we know what that is, okay? So if I look at this function, the first thing I notice is that it has a negative leading coefficient. That's the value of a. So that tells me that this parabola is going to open down. That's just good information to have, okay? Now, the vertex is going to be, just like with transformations, h is always going to flip the sign. So since I see x minus 3, my h value is positive 3, and then k you always keep the same, so 8. 3, 8 is my vertex. So I'm going to start by making a table of values, okay? And the first point is going to be what I already know, the vertex 3, 8. I always count to the right, but you can certainly go to the left. So then I'm going to choose 4 and 5. I just need to get 2 points on one side of my vertex. And so I'm just going to plug those in. So if I plug in 4, I'm going to get negative 2 times 1 squared plus 8, so that'll be 6. And if I plug in 5, I'm going to get negative 2 times 2 squared plus 8. 2 squared is 4. 2 times negative 2 is negative 8. And so, plus, we get 0. So here's what I've got. 3, 8 is my vertex. The axis of symmetry is this invisible vertical line through here. Now, you don't have to draw it, but that is what we're looking at. And then I plot those other 2 points, 4, 6 here, and 5, 0 here. Now, I'm going to take those points and reflect them to their mirror image on the other side of my axis of symmetry. And then we're going to connect with a smooth curve like this. So there is our parabola. Now we can tell a lot of things by looking at this. Again, the axis of symmetry is going to be the equation x equals 3, because that's the h value. I can also see the domain is negative infinity to positive infinity, but I can also tell the range, which is negative infinity up to 8. Now, you can tell that without even having to graph it by knowing that the vertex is at 3, 8, and it opens down, so that's my highest y value. It has a maximum instead of a minimum, okay? So that's just a quick refresher on how to do that in vertex form. All parabolas are pretty much the same. Figure out where the vertex is and then get 2 other points. Finding the vertex is a little different depending on the form you're in, but that's how we do it in vertex form. Let's talk about how we would do it in standard form. Okay, so standard form is when everything is multiplied out. Ax squared plus bx plus c is our standard form. It's what we want if we do quadratic formula or anything like that. So the vertex, the x value, it actually starts with this axis of symmetry equation. The axis of symmetry defines the value of x. X is equal to the opposite of b divided by 2a. Once I know what x is, then I plug it in to the function to figure out the value of y. That's all that means, okay? And then a handy thing to know is this plus c at the end will always be your y-intercept. So that's a point that we know automatically, okay? So it's a good thing to keep in mind. Now the process for graphing this is going to be very much the same. We start by finding the vertex. Once I have that, then I'm going to pick 2 points to the right, figure those out, reflect it, and graph the whole thing. So let's look at example 2. F of x is equal to negative x squared plus 4x plus 1. We want domain and range from the graph. Okay, so the formula to figure out x is the opposite of b over 2a. b is 4, so I get negative 4 over 2 times a, which is negative 1. So 4 divided by negative 2 is 2. What I know from that is that our axis of symmetry is x equals 2. But to figure out the vertex, now I need to plug in f of 2, and that's going to be negative 2 squared plus 4 times 2 plus 1. 2 squared is 4. The opposite is negative 4. Negative 4 plus 8 is 4 plus 1 equals 5. This tells me that my vertex is 2, 5. Again, 2 is what we plugged in. 5 is what we got out. So that's our vertex, 2, 5. And once we know that, just like on the other one, we're going to pick a couple of points. I already know 2, 5. Then maybe I'll plug in 3 and 4 again. If you would rather plug in 1 and 0, that might be easier to plug in this case. So maybe you want to work backwards instead. That would be fine. You'd get the same thing. You'll get the left half instead of the right half like I'm going to get here. Okay, so we're just going to plug these numbers in. When I plug in 3, you should get 4. And when I plug in 4, we should get 1. So those are our ordered pairs. So we'll start at 2, 5. Again, that's our vertex. Then I'll go to 3, 4. And I'll go to 4, 1. And it does make sense that this parabola is opening down because of the negative leading coefficient. Reflect it back so it's symmetric. Whoops, that's in the wrong spot. Symmetric. And then connect with a smooth curve. Domain and range. There we are. You can tell by the graph. If it opens downwards, it's always going to start from negative infinity for the range. If it opens upward, you'd start at the number and go towards positive infinity. The last thing that I just want to quickly show you is revisiting piecewise functions, because this information is going to be really helpful if we have quadratic pieces in our piecewise function, okay? Whoops. So when I look at this first one here, x squared minus 2, I know that that's going to be a parabola. And I know that that is a parabola with a vertex at 0, negative 2. H is 0, k is negative 2. And 0 is not greater than or equal to negative 1. So that means I'm not going to hit, 0 is greater than negative 1. So my vertex is going to be included. So when I choose values for this first one, x and x squared minus 2, okay, I'm going to choose negative 1 because that's our boundary point and it's going to be an open circle there. Then I definitely want to pick 0 because I need to know where my vertex goes. I already do know that it's at 0, negative 2. And then maybe I'll pick one more on the other side. Maybe I'll pick 1 or 2. We can pick 1 so that we see what we've got. Again, this is what we knew from up here. You've got to know where your vertex goes. Otherwise, if you just pick 2 points, you might think you have a straight line. So -1, when I plug that in, we're going to get 1 minus 2, which is -1. +1 is going to do the same thing. So we can graph -1, -1 with an open circle, 0, -2 with a closed circle, and then 1, -1 with a closed circle. So this side of the graph is going to go like this. If I hadn't done that vertex, I might think it's a horizontal line or some other line. I might have thought it was a diagonal line, because we just got to make sure we know what we know about parabolas so we can get all the pieces. This middle piece is weird. It's equal to 4 only when x is equal to -1. Well, that would just be a dot. If x equals -1, the function is equal to 4. That's all we get. And then for the other one, we're again going to start at -1. And this one is a line, so I just need one other point, maybe at, oh, we're going less than -1, so that won't work. Let's do -2, because that's less than -1. So -1 gives us -3, -2 gives us -4. This is going to be an open circle again, because it's not equal to. So -1, -3, -1, -3, open circle here. And then -2, -4, -2, -4, and this one is a line. So that is what our graph would look like, okay? Domain should be pretty straightforward, -infinity to +infinity. The range is going to be a little bit different because, again, we skip this chunk of the graph right here, so you have to hop over it. There's no function between -3 and -2 on the y values. So that would be our domain and range. So it's just a little reminder with piecewise. The vertex is always going to be important information. So that's it. Quick little refresher on graphing parabolas, and you should be able to do the first half of your worksheet based on that.